In the annals of human endeavor, the Apollo missions are often remembered for their dramatic lunar landings and the triumphant planting of flags. Yet, beneath these iconic images lies a less visible, but equally profound, scientific legacy. From 1969 to 1972, 5 Apollo missions deployed sensitive scientific instruments designed to listen to the moon's interior. This silent vigil, lasting for years after the astronauts departed, began to reveal a dynamic, seismically active celestial body, challenging our initial perceptions of a tranquil, unchanging lunar landscape. It was a testament to the foresight of those who understood that true exploration extends far beyond surface observations. Central to this long-term observation was the Apollo Lunar Surface Experiments Package, or ALSEP. This self-contained suite of instruments, powered by radioisotope thermoelectric generators, was left behind by astronauts from Apollo 11, 12, 14, 15, and 16. Among its key components was a passive seismometer, meticulously designed to detect the faintest tremors originating from within the moon or from impacts on its surface. The ALSEP network represented an unprecedented commitment to long-duration extraterrestrial scientific data collection, providing a continuous acoustic window into the moon's deep structure. The ALSEP seismometers proved remarkably resilient. From their deployment in 1969 until their deactivation in 1977, they transmitted a continuous stream of data back to Earth, totaling 8 years of uninterrupted seismic monitoring. This extensive dataset allowed scientists to build a comprehensive picture of lunar seismic activity, a feat impossible with short-duration missions. Researchers, including those at Lamont Doherty Earth Observatory, carefully cataloged thousands of events, providing the first detailed insights into the moon's internal dynamics and its interactions with Earth. Contrary to some initial assumptions of a geologically dead world, the ALSEP data conclusively demonstrated that the moon is seismically active. Scientists identified several distinct categories of moonquakes, each with its own unique characteristics and origins. This revelation opened up entirely new avenues of research into lunar geology, suggesting that internal forces and external influences continue to shape our celestial neighbor. The sheer volume and consistency of the data allowed for this nuanced classification, providing a blueprint for understanding other planetary bodies. The most frequently detected events were deep moonquakes, accounting for approximately 70% of all recorded seismic activity. These quakes originate far beneath the surface, at depths ranging from 700 to 1200 kilometers. Researchers quickly attributed their cause to tidal stresses exerted by Earth's powerful gravity, an effect similar to how the moon causes tides on Earth. These deep moonquakes often occur in distinct clusters, typically following monthly cycles that correlate precisely with the moon's perigee, its closest approach to Earth, demonstrating a direct gravitational link. In contrast to their deeper counterparts, shallow moonquakes are much rarer, with only 28 events detected throughout the 8-year monitoring period. However, what they lack in frequency, they make up for in intensity. Occurring at depths between 20 and 30 kilometers, these quakes are thought to be of tectonic origin, similar to earthquakes on Earth, involving the movement of fault lines. Scientists estimate their magnitudes can reach up to 5.5 on the Richter scale, making them significantly more powerful than any other type of lunar seismic event. Their infrequency continues to pose a challenge for detailed study. Beyond the internal quakes, ALSEP also recorded events attributed to external and surface-level phenomena. Thermal quakes are weak, shallow seismic events caused by the extreme temperature fluctuations between lunar day and night. As rocks rapidly heat and expand, then cool and contract, stress builds and releases, creating minor tremors. Additionally, the instruments meticulously documented thousands of meteoroid impacts. These surface events were easily distinguishable by their unique seismic signatures, providing valuable data on the flux of small celestial bodies impacting the moon. For decades, the prevailing scientific consensus characterized the moon as an utterly dry celestial body. This view was largely based on the initial analysis of Apollo rock samples, which showed no detectable water, and the high temperatures and vacuum conditions on the lunar surface, making liquid water impossible. The early missions reinforced this image of an arid, barren world. The absence of water had profound implications for future lunar exploration, suggesting that any sustained human presence would require complex and costly systems to transport water from Earth, or produce it through unknown means. The Apollo 17 mission, launched in 1972, stands out as the only Apollo flight to include a trained geologist, Harrison Jack Schmitt, among its crew. Schmitt's expertise brought a unique perspective to lunar exploration, allowing for on-the-spot geological analysis and more targeted sample collection. During their EVA activities, the Apollo 17 crew deployed an active seismic experiment, which involved detonating small explosive charges to create seismic waves that probed the shallow subsurface. This active approach provided additional, direct measurements of the lunar crust's properties, complementing the passive listening of ALSEP. During the post-mission analysis of lunar rock samples brought back by Apollo 17, scientists observed trace amounts of what appeared to be water. However, in line with the prevailing dry moon hypothesis, these detections were largely dismissed. The scientific community at the time widely attributed these minor findings to contamination. Researchers believed that the water had either originated from Earth's atmosphere, clinging to the samples during their return journey, or was introduced during laboratory processing. This attribution reinforced the existing paradigm, pushing any notion of lunar water to the periphery of scientific thought. The prevailing view of a bone-dry moon persisted until a pivotal mission in 2009, the Lunar Crater Observation and Sensing Satellite, or LCROSS. NASA intentionally crashed the upper stage of its Centaur rocket, followed by the LCROSS spacecraft itself, into a permanently shadowed crater near the Moon's south pole. The target, KBSA, was selected precisely because its perpetual darkness promised to harbor volatile compounds, shielded from the sun's heat. This daring, sacrificial mission was designed to create an impact plume visible from Earth, allowing for spectroscopic analysis of ejected material. The LCROSS mission delivered groundbreaking results. On October 9, 2009, the Centaur rocket slammed into KBSA, creating a plume of debris. Immediately following, the LCROSS spacecraft flew through the plume, collecting crucial data before its own impact. Scientists analyzing the spectroscopic signatures of the ejected material unequivocally confirmed the presence of significant quantities of water ice. This discovery fundamentally challenged the long-held assumption of a desiccated moon, providing direct, undeniable evidence that water, in frozen form, was present in lunar polar regions. The definitive evidence from LCROSS prompted a critical re-evaluation of previous Apollo mission data, especially the Apollo 17 rock samples. With the understanding that the moon could indeed harbor water, scientists revisited those initial trace detections that had been previously dismissed as contamination. This time, armed with more sensitive analytical techniques and a new theoretical framework, researchers looked beyond the surface-level assumptions. It was an example of how new discoveries can force a reinterpretation of old evidence, unveiling truths that were once obscured by prevailing paradigms. The re-examination yielded remarkable results. Scientists discovered tiny volcanic glass beads within the Apollo 17 samples, dating back billions of years. Crucially, these beads contained minuscule amounts of water trapped within them. Because these glass beads formed during explosive volcanic eruptions deep within the moon's interior, the water found inside them was unequivocally of lunar origin, shielded from terrestrial contamination. This discovery provided compelling evidence for ancient water within the moon's mantle, suggesting the moon was not entirely dry at its formation or early history, a truly revolutionary concept. The confirmation of both surface ice and ancient interior water has profound implications for future lunar exploration and colonization. Lunar water ice, particularly at the poles, is now recognized as a critical in situ resource. It can be harvested for drinking water, providing life support for future lunar bases. Furthermore, it can be broken down into hydrogen and oxygen, serving as rocket fuel for missions departing from the moon, effectively transforming the moon into a refueling depot for deep space travel. This dramatically reduces the cost and complexity of sustained lunar presence. While water offers opportunities, the seismic data from ALSEP also highlights potential challenges. The powerful shallow moonquakes, though rare, reaching magnitudes up to 5.5, could pose a significant risk to future lunar habitats and infrastructure. Designing structures that can withstand such tremors, especially in regions prone to these events, will be crucial for the safety and longevity of lunar outposts. Furthermore, the constant, though weaker, deep moonquakes must also be considered in long-term engineering plans. Understanding these seismic hazards is vital for mitigating risks. The extensive ALSEP seismic data continues to be invaluable for refining models of the Moon's interior structure. By analyzing how seismic waves travel through the Moon, reflecting, refracting, and attenuating, scientists can infer the properties and composition of its crust, mantle, and potentially its core. The distinct characteristics of deep and shallow moonquakes, combined with meteorite impact data, provide vital constraints for these models, helping us to understand the Moon's thermal history, differentiation, and evolution. This foundational knowledge is crucial for a complete picture of planetary formation. The story of seismic whispers beneath the Moon is a powerful reminder that scientific discovery is rarely a finished chapter. The Apollo missions, often celebrated for their initial triumph, established a platform for continuous learning. 8 years of ALSEP data and the later re-evaluation of Apollo rock samples, spurred by new missions like LaCrosse, have profoundly reshaped our understanding of the Moon. From a dry, static orb to a seismically active body harboring vital water resources, the Moon continues to reveal its secrets, proving that foundational science can yield breakthroughs decades later.